Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistor physics perspective, lecture number 30, and the topic of the lecture is leakage in MOSFETs. So what we intend to do is that we have actually taken care of understanding of basics of MOSFETs. We have also understood the basics of homojunction p-n junction diode and its theory, and a heterojunction p-n junction diode and its theory. Now what we will be entering into is the actual area in which this series was actually developed, that you should be able to appreciate the next generation FET devices which will be coming into picture for circuit applications. In order to appreciate that, from week 6 we will be starting the next set of lectures on more than Moore era sort of MOSFET. But in order to appreciate that and to get the whole picture in a proper sense, we thought of introducing a week where you should be able to understand the short channel effects, or basically the second order effects in MOSFETs, right. So in order to appreciate that point, let us start with today's lecture. Let me explain to you what is a short channel effect, right. So the idea is that till now, if you look very clearly in our whole lecture series, we were saying that my channel length was large and my width was also very large, which means that my L and W is relatively very large. Maybe L is of the order of few microns and W is of the order of few microns, right. They are of the order of microns, which means that, as I discussed earlier, gradual channel approximation is applicable and there is concept of inverse narrow width effects, right. There is no concept of inverse narrow width effects coming into picture because of a larger width in this case. The idea was that therefore the mathematics is very easy to handle, but the problem is that as you start to reduce the dimensions of the device for the reasons well known to you, if you follow Moore's law you have to do that, which means you are trying to bring the source and drain closer and closer to each other. The obvious question asked is, till what distance can you bring them closer? Well, ideally the distance should be equals to 0, because when you bring them closer they will short and you will never have a FET device available to you. So practically how much amount of source and drain region need to be closer together in order to let it work still as a MOSFET. But however, when you start to bring them closer, you have these problems of short channel effects, velocity saturation, CLM, channel length modulation. Your source drain resistance effectively becomes of the order of the channel resistance, and there is a breakdown because of high electric field which happens. So the idea behind the study of second order effects or short channel effect is to give you roughly an idea how, with reducing value of the channel length, what problems which you leave. In that whole segment, we will be just looking into this lecture on the threshold voltage effect and the leakage phenomena in MOSFET. Within leakage, we will be studying what are the sources of leakage: subthreshold leakage, gate and junction leakage, right. And these are all off currents, right. Off current basically means when the device is off and your gate voltage is not more than the threshold voltage of the device is basically in the off state. However, it is still giving some current, and that current will be defined as the leakage current, right. So let us look at the threshold voltage effect and see how it works out. We have already understood that if you take up on the right hand side you see a bulk enhancement mode MOSFET, N channel, because you have a p type substrate here, and what happens is that interestingly, that if you have N plus region here and N plus region here, there will be a depletion region which will be formed with the p layer here, and there will be a depletion region which will be formed here with p region, N plus and p. So there will be an N plus p depletion region which will be formed, right. And similarly on the right hand side there will be also an N plus p depletion layer which will be formed. So this is referred to as XDX and this is never the XDD, depletion width on the drain side, depletion width on the source side. Obviously if you apply a bias now on the drain side, the depletion width there will be larger, which means that under bias conditions, under VDS, let us suppose, my XD of D will be larger than XD of S, right, and that is there, right, that XD of D is much larger as compared to XD of S, right. Now The reason for this is that the drain side is much more reverse biased, and therefore if you look carefully, this is my del LD, which is mean the reduction in the actual channel length because the depletion region has eaten away into the inversion layer. Similarly, this is the amount of eating away of the inversion layer on the source side, right. However, that will be small, this will be relatively large, right, and as a result your effective channel length will actually reduce in a sense as you go on increasing the value of VDS. That is what is known as CLM. We have already discussed this point. However, till now we were assuming that the threshold voltage is constant, right, ideally, and it is independent of any factor available. But as you change the dimension of the device as well as the doping, because when you scale down the device you also scale the doping, and therefore the doping concentration changes, and the doping concentration changes, you either require a larger or a smaller gate voltage to form the inversion layer, and therefore the threshold voltage becomes a function of the doping concentration and the channel length, right, and this is known as channel roll off or threshold voltage roll off, right. So ideally we assume that threshold voltage will be constant. In reality not true, they will be changing with respect to biases, right. So let us come to the first leakage in a MOSFET, right. If you look carefully in this case, this is my source on the drain side and the gate side. If you apply a positive bias here, and even if you ground this body here, you will have a direct tunneling between the oxide layer and it will go down here. This is known as a tunneling current, gate tunneling current or direct tunneling current. Similarly, when your drain voltage is very small and it is very close to the value of the source voltage, which means DS is almost close to Vs, right. When the drain voltage is very close to the source voltage, since electric field is small, it will not be drift induced, it will be diffusion. When there will be diffusion, there will be always a subthreshold current which will be flowing through the device, right, and the subthreshold current will be acting as a leakage current. Similarly, I can also have an N plus into the junction leakage. This is known as junction leakage. Why? Because it is basically a PN junction diode in reverse biased. Refresh your memories about PN junction diode working as a reverse biased PN junction diode. Remember, the majority will never contribute in the PN junction diode, but minority will actually contribute and give you a current source. So that is the reason you will always get a current here, and that is known as a junction current. So I have a junction current which is flowing from drain onto the substrate. Source to substrate it will not flow because source and body are always on the same potential in more case than other. However, there will be another component which is gate to body, which is direct tunneling through the oxide layer if the oxide layer goes very thin, and there will be a subthreshold current which will be flowing from drain to source. Look at the right hand side figure. What we have done is that we have plotted IDS with respect to VGS. It is a log scale. So if you look very carefully, this is your log scale here, and as you can see here that this is the region between this Vg and this Vg, you have subthreshold region. So what is the subthreshold region? Where your gate voltage is just below. So threshold voltage in this case is considered to be approximately equals to 0.3 volts. So any voltage less than 0.3 will be defined as subthreshold, above that will be known as saturation or post threshold. Now, so if you look, you see your VDS, as the VDS is increased from 0.1 to 1 volt, your off current has actually increased from 2 nanoampere per micrometer normalized with respect to width to approximately 27 nanoampere per micrometer. So if your width is let us say 1 micron, then typically if you raise your VDS from 0.1 to 1 volts, your leakage current at 0 bias. So at 0 bias you expect the device to be off? No, but what is happening is that for a low value of VDS equals to 0.1, you get 2 nanoamperes of current. For 1 volt you get about 30 nanoamperes of current, or even 27-28 nanoamperes of current. Looks small, but if you multiply that with resistance and over a period of time it is flowing, the total power will be typically very large. I will not discuss this jiddle and biddle, we will discuss it later on as we move ahead. This is drain induced barrier lowering, and as you increase the drain voltage, your subthreshold leakage current also increases to a large value, right, and that is the problem area of leakage of MOS devices. So as I discussed with you, the main sources of leakage are transistor going from on to off, and that is basically the subthreshold leakage, and it is obviously the dominant leakage source in current transistors. You have a gate leakage because when you have an ultra thin gate oxide or the gate oxide thickness is very small, you will have a large leakage which is happening, and this is known as direct tunneling. I already discussed with you, junction leakage is primarily reversed bias PN junction diode current which is flowing between the drain and the substrate, source and the substrate. Now let me come to the body or substrate effect. So we have understood the other effects, let me come to that. As I discussed with you, that substrate is considered to be the fourth terminal of MOSFET. So you have source, drain and gate are the three terminals, but substrate is also the fourth terminal, and the reason being very simple, that if you apply a bias on the substrate side, on the source, on the substrate side, let us see what happens. Let me show you the diagram here. Let me rub this point and explain to you. Let me apply a positive bias here, and the gate voltage is larger than threshold, a very thin inversion layer which is being formed here, right. Now from where did you get the charge? You got the charge from this region, from this region and from this region. So there was an initial electric field which was coming in this direction when VB was equals to 0. When you make VB positive, this electric field will reduce, effective electric field in the transverse direction will reduce, or I can say there will be another electric field which will be pushing the holes from the substrate onto the inversion layer, right. So that is the problem when you have the substrate effect, which means that the substrate can actually change the threshold voltage of the device, right. Substrate can actually change the threshold voltage of the device. Now in most of the cases, if you short source and bulk or you make them grounded, then this effect will not be there. But if they are not shorted or grounded, and if there is a difference between the source and bulk potential or even gate and bulk potential, you will have this change in the threshold voltage, and that is given by this expression here, that the if you have VSB as the source to bulk voltage, if this is 0, you see, you will see that this quantity goes to 0, root phi s minus root phi s is 0, and therefore this quantity does not play any role. Your Vt is equals to Vt 0. What is Vt 0? Vt 0 is a threshold voltage where when VSB equals to 0. So what is Vt 0? Vt 0 equals to Vt at VSB equals to 0. So when you do not have any substrate effect or body effect, the value of Vt 0 is equals to Vt, where gamma is known as a body coefficient or body factor, and then phi s is given, the surface potential is given by this formula and gamma is given by this formula. Do not worry from where we are getting it, it is all given in the standard books with us. However, one thing to be noted therefore is, as you make the VSB larger and larger, you see your Vt becomes larger and larger, which means that as the VSB value, how do you define VSB? VSB is defined as Vs minus Vb. So source potential minus the bulk potential. As this value goes on increasing, it can only increase when you make your Vb smaller or Vs larger. Either of the two cases, the threshold voltage will go on increasing. Now for a when your VSB is very small, then we take this into consideration, this formula into consideration, and when VSB is large, we take this into consideration, right. At this stage, again, what I have written here, you just assume it to be true and move forward, taken from any of the standard books only. Let me come to the subthreshold leakage. Now as I discussed with you, this will be small amount of current will be flowing from source to drain of a MOSFET even when the transistor is in the off state, and the value of the drain current here is given by this expression here, and as you can see, it is exponentially depending thing. Even if you forget about this particular point, this is an exponential depending on the value of VDS. So when VDS goes on becoming higher and higher, e to the power minus VDS goes on reducing, and 1 minus this goes on increasing, and therefore IDS goes on increasing, right. So how do you define subthreshold slope now? Subthreshold slope is defined in this manner. If you come back here and if you take let me rub this thing, if you take the slope of this curve, right, then we define subthreshold slope as the amount of change, right, in gate voltage for a decade change in the drain current. So one decade change which you see will give you the, so basically the slope of this curve, if you find out, it will be basically del Vg del Id, right. So we take 1 over the slope of this one will give you the subthreshold slope, and that is what I have written here, that it is called the slope of the line, the similar. So the inverse of the slope of this line is called the subthreshold slope and is given by n times Vt. Vt is the thermal equivalent voltage ln of 10 which you get, right, 2.303 or something like this. and similarly in subthreshold current you get this log scale slope current you get. Let me come to the gate leakage current. As I discussed with you, when the oxide thicknesses are very small, of the order of 15 to 20 angstrom approximately, there will be some tunneling phenomena taking place from the gate to towards the channel side, and when it reaches the channel it will be drawn by the drain voltage, and this is known as the gate leakage current. Two physical mechanisms are responsible. One is known as the Fowler-Nordheim tunneling. This happens when the oxide thickness is large, and you have a direct tunneling when you have an ultra thin oxide available to you. And we define the gate current to be in this manner. Okay, the expression for the gate current, where A and B are constant, W is the width, A and B are constant depending upon the technology, and that gives you a basic idea about the gate current. And as you can see, as the value of your VDD goes on increasing, the drain to source voltage goes on increasing, your gate leakage current also tends to become more. So one way, good idea to reduce your off state power or off state leakage is to reduce the potential, but once you do that there will be other problems coming into picture, but just for gate leakage reduction of VDD is an important point. Junction leakage is basically when you have a PN junction diode formation or a PN junction depletion region formation, there will be diffusion, and therefore there will be a reverse current which will be flowing, and it is given by as ID equals to Is e to the power Vd by Vt minus 1, where Vd is the applied reverse bias voltage, Vt is the thermal equivalent voltage which is Kt by Q, 25 millivolts at 300 Kelvin, and Is is the reverse saturation current, right, and therefore this gives you the leakage current, and it depends upon obviously on the temperature also. So as the temperature goes on increasing, you will see that this quantity goes on increasing, right. When this quantity goes on increasing, this quantity goes on decreasing, which means that this quantity goes on decreasing, that minus 1 will go on decreasing. So at higher temperature the junction leakage will have a lesser amount of contributory role to the total leakage current flowing through the device. This is just to, before we end the lecture, consider this is a small threshold voltage problem, and we are just finding out how much threshold voltage will change at 300 Kelvin if the source is changed from 0 volt to 0.6 volts. So you just need to put in that formula and get the value. So what you do is you first try to find out the surface potential. How will you find the surface potential? Surface potential is given by this formula here, this one, and then you need to find out gamma. Take these two together and plug it here, right, and so what you get from here is that you get the value of phi s to be equals to 0.93 volts, the value of gamma to be equals to the value of 0.93, value of gamma is 0.16, and then you take these two values and place it at the expression which we know. So it is 0.3 plus gamma times root phi s plus VSB minus root phi s, and it comes out to be 0.34, which you see quite interestingly that when the source voltage is changed from 0 to 0.6, your threshold voltage changes from 0.3 to 0.34. This was what I was talking about when we are saying you have a substrate effect into consideration. So with this, let me recapitulate what we did for this lecture. We looked into the second order effects, right, second order effects or short channel effects, and we looked into the first, and then we looked into the MOSFETs second order effects, for example threshold voltage, and we looked into how threshold voltage is depending on the value of VSB, and we did a numerical problem to solve it to show you that there will be a threshold voltage change because of the source voltage change. We also looked into the various leakage currents, right, leakage currents which we follow in a MOSFET. We looked into that, and we saw that which one is most prevalent under which conditions, right, and that will give me an idea about what problem statements we can have when your devices are run at either very low values of voltages, or the devices have gone to such a small level that the electric field is quite large, right. So this will be useful when we take up the next part of our lecture series on gate all around devices. With this, let me thank you for your patient hearing. Thank you.